Identity: anything that can get authenticated is an identity. It could be a user, an application, or server that gets authenticated through username/pwd or secret or digital signatures. Account: an identity that has data associated with it. You cannot have an account without an identity. Azure AD: account: an identity created through Azure AD or another Microsoft Cloud service, such as Microsoft 365. Identities are stored in Azure AD and accessible to your organization's cloud service subscriptions. This account is also sometimes called a work or a school account. Azure subscription used to pay for Azure cloud services. You may have many subscriptions and they are linked to a credit card. Azure Tenant: a dedicated and trusted instance of Azure AD that is automatically created when your organization signs up for a Microsoft Cloud Service subscription, such as Microsoft Azure, Microsoft Intune, or Microsoft 365. An Azure tenant represents a single organization Azure AD directory. Each Azure tenant has a dedicated and trusted AD directory. The Azure AD directory includes the tenant's users, groups, and apps and is used to perform IAM functions for tenant resources. Management groups: if your organization has several subscriptions, then management group helps you manage access, policies, and compliance for those subscriptions. Management group is a level of scope above subscriptions. Subscriptions are organized into containers called management groups and apply your governance conditions to the management groups. Management groups enable a. Organizational alignment for your Azure subscriptions through custom hierarchies and grouping. b. Targeting of policies and spend budgets across subscriptions and inheritance down the hierarchies. c. Compliance and cost reporting by organizations. Resource group: fundamental element of Azure platform. A resource group is a logical container for resources deployed on Azure. These resources are anything that you create in Azure subscription like VM, gateways, DBS, etc. All resources must be in a resource group and a resource can only be a member of one resource group at a time. Many resources can be moved between resource groups. Resource groups cannot be nested. Before any resource can be provisioned, you need a resource group for it to be placed in. If you delete a resource group, all resources contained within are also deleted. RBAC: roles and permissions can be given at resource group level. Resource groups helps in managing life cycle of resources, authorization of resources, monitoring of resource usage and resource billing. Azure limits are called quotas. Currently, you cannot use Resource Manager templates to create management groups. Management groups can be nested, but resource groups cannot be nested. Resource group is a logical container for resources deployed on Azure. AAD is an IaaS, infrastructure as a service. Resource groups are a scope of RBAC. Azure AD defines users in three ways: a. Cloud identities, b. Directory synchronized identities, c. Guest users. Azure AD allows you to define two different types of groups: a. Security groups, to manage member and computer access to shared resources for a group of users, b. Microsoft 365 groups, to provide collaboration opportunities by giving members access to a shared mailbox, calendar, SharePoint, etc. There are three different ways you can assign access rights: a. Assigned, b. Dynamic by looking at members' attributes for dynamic membership, c. Dynamic device, for adding and removing devices to security groups. There is no parent-child relationship between tenants. This independence between tenants includes resource independence, administrative independence, and synchronization independence. Resource independence: if you create or delete a resource in one tenant, it has no impact on any resource in another tenant, with the partial exception of external users. If you use one of your domain names with one tenant, it cannot be used with any other tenant. Administrative independence: if a non-administrative user of tenant Contoso creates a test tenant test, then, by default, the user who creates a tenant is added as an external user in that new tenant, and assigned the global administrator role in that tenant. The administrators of tenant Contoso have no direct administrative privileges to tenant test, unless an administrator of test specifically grants them these privileges. However, administrators of Contoso can control access to tenant test if they control the user account that created test. If you add/remove an administrator role for a user in one tenant, the change does not affect the administrator roles that the user has in another tenant. Synchronization independence. You can configure each Azure AD tenant independently to get data synchronized from a single instance of either the Azure AD Connect tool, to synchronize data with a single AD forest. The Azure Active Tenant Connector for Forefront Identity Manager, to synchronize data with one or more on-premises forests, and /or non-Azure AD data sources. Tenants are not part of Azure subscription. If an Azure subscription is cancelled or expired, you can still access your tenant data using PowerShell, Microsoft Graph API or the Microsoft 365 admin user. By default, when you create an Azure subscription, an Azure AD domain is created for you. This instance of the domain has initial domain name in the form domainname.onmicrosoft.com. Although the initial domain name for a directory can't be changed or deleted, you can add any routable custom domain name you control. This simplifies the user sign-on experience by allowing user to log on with credentials they are familiar with. For example, a contosogold.onmicrosoft.com could be assigned a simpler custom domain name of contosogold.com. Only a global administrator can perform domain management tasks in Azure AD. By default, this is the user who created the subscription. Domain names in Azure AD are globally unique. If one Azure AD directory has verified a domain name, then no other Azure AD directory can verify or use that same domain name. Before a custom domain name can be used by Azure AD, the custom domain name must be added to your directory and verified. Conditional access is the tool used by Azure Active Directory to bring identity signals of user membership of a group, user location, user application, and user device together to make decisions and enforce organizational policies. Conditional access policies at their simplest are if-then statements. If a user wants to access a resource, then they must complete an action. Conditional access policies are enforced after the first factor authentication has been completed. Conditional access is not intended as an organization's first line of defense for scenarios like denial of service attacks, but can use signals from these events to determine access. With named locations, you can create logical groupings of IP address ranges or countries or groups. The number of days before a user must re-authenticate on trusted devices can also be configured with the value from 1 to 60 days. Default is 14 days. Virtual networks, VNets, are used in Azure to provide private connectivity between Azure virtual machines and other Azure services. VMS and services that are part of the same virtual network can access one another. By default, services outside the virtual network cannot connect to services within the virtual network. VNet is scoped to subscription. VNet is scoped to a single region/location. One region can have many VNets and one subscription can have more than one VNets. A VNet cannot span different regions/locations. However, VNets of different regions can be connected together using virtual network peering and VPN gateways. When creating a VNet, you must specify a custom private IP address space using public and private addresses. Azure assigns resources in a virtual network a private IP address from the address space of the VNet. Azure will treat any address range as part of the private VNet IP address space if it is only reachable within the VNet, within interconnected VNets, and from your on-premises location. By default, there is no security boundary between subnets, so services in each of these subnets can talk to one another. NSGs act as software firewalls, applying custom rules to each inbound and outbound request at the network interface and subnet level. This allows you to fully control every network request coming in or out of the VM. The choice of Azure location for any service or resource must be made keeping in mind the hardware requirements and configurations of your project and pricing differences. An Azure resource is a manageable item in Azure. If Azure creates the resource, it will use the VM name to generate the resource name. The workload options while selecting a VM are general purpose, compute optimized, memory optimized, storage optimized, GPU, high performance computers and confidential compute, designed to protect the confidentiality and the integrity of the data and code while it is processed in the cloud. The VM size can be changed while the VM is running, as long as the new size is available in the current hardware cluster the VM is running on. The Azure portal makes this obvious by only showing the available size choices. The command line tools will report an error if you attempt to resize a VM to an unavailable size. Changing a running VM size will automatically reboot the machine to complete the request. If you stop and deallocate the VM, you can then select any size available in your region since this removes your VM from the cluster it was running on. For every VM, there will be two separate costs, compute costs and storage costs. Your subscription will be charged. By separating these costs, you scale them independently and only pay for what you need. Compute costs are priced on a per-hour basis, but billed on a per-second basis. The hourly price varies based on the VM size and OS you select. The cost of VM includes the charge for Windows OS. Storage costs are charged separately for the storage VM uses. If you stop and deallocate a VM, compute costs are not charged, but storage costs are still charged. The reserved virtual machine instances, RI, option is an advance purchase of a virtual machine for 1 or 3 years in a specified region. The commitment is made up front, and in return, you get savings up to 72% compared to pay-as-you-go pricing. RIs are flexible and can easily be exchanged or returned for an early termination fee. Prefer this option if the VM has to run continuously, and you need budget predictability. Spot pricing is purchasing an unused compute capacity at discount. Spot VMs are workloads that can be interrupted, providing scalability while reducing costs. Azure Hybrid benefit is for customers who have licenses with software assurance, which helps maximize the value of existing on-premises Windows Server and /or SQL Server license investments when migrating to Azure. Azure only supports 64-bit operating systems. All Azure virtual machines will have at least 2 virtual hard disks, VHDs. The first disk stores the operating system, and the second is used as temporary storage. Additional disks can be added to store application data, the maximum number of which is determined by the VM size selection, typically 2 per CPU. The data for each VHD is held in Azure Storage as page blobs. Temp storage is not preserved. Azure Storage is Microsoft's cloud-based data storage solution that supports any type of data. A storage account provides access to objects in Azure Storage for a specific subscription. VMs always have 1 or more storage accounts to hold each attached virtual disk. Virtual disks can be backed by either standard or premium storage accounts. Azure Premium Storage leverages solid-state drives, SSDs, to enable high performance and low latency for VMs running I/O-sensitive workloads. Managed disks are the newer storage model, which are block-level storage volumes that are managed by Azure and used with Azure virtual machines. Managed disks are like physical disks in an on-premise server but virtualized. A resource group is a logical container that holds related Azure resources. Resource groups allow you to deploy and monitor resources as a group and track billing costs by resource group. An availability set is a logical grouping of VMs within a dataset that allows Azure to understand how your application is built to provide for redundancy and availability. There is no cost for the availability set itself, you only pay for each VM instance that you create. In an availability set, VMs are automatically distributed across these fault domains. This approach limits the impact of potential physical hardware failures, network outages, and power interruptions. For VMs using Azure Managed Disks, VMs are aligned with managed disk fault domains when using a managed availability set. This alignment ensures that all the managed disks attached to a VM are within the same managed disk fault domain. Only VMs with managed disks can be created in a managed availability set. The number of manager disk fault domains varies by region. Fault domains are vertical, update domains are horizontal. VMS within an availability set are also automatically distributed across update domains. An availability zone is a physically separate zone, within an Azure region. There are 3 availability zones per supported Azure region. Availability zones expand the level of control you have to maintain the availability of the applications and data on your VMS. Each availability zone has a distinct power source, network, and cooling. A fault domain is a logical group of underlying hardware that share a common power source and network switch, similar to a rack within an on-premise data center. An update domain is a logical group of underlying hardware that can undergo maintenance or be rebooted at the same time. This approach ensures that at least one instance of your application is always running. The order of update domains being rebooted may not proceed sequentially during maintenance, but only one update domain is rebooted at a time. Vertical scaling, known as scale up or scale down, means increasing or decreasing the virtual machine sizes in response to workload. No new virtual machines are created in virtual scaling up. Horizontal scaling, also referred as scale out or scale in, where the number of VMS is altered depending upon the workload. Virtual scaling has more limitations in terms of hardware, CPU, etc. Vertical scaling also requires a virtual machine to stop and restart. Horizontal scaling is more flexible. Reprovisioning means removing an existing virtual machine and replacing it with a new one. Azure Virtual Machine Scale Sets let you create and manage a group of load-balanced VMS, whose number may vary according to workload or a defined schedule. Scale sets provide high availability to your applications and allow you to centrally manage, configure, and update many VMS. There is no cost for the scale set itself, you only pay for each VM instance that you create. Virtual machines in a scale set can be deployed across multiple update domains and fault domains to maximize availability and resilience to outages due to data center outages and planned or unplanned maintenance events. Virtual machine scale sets simplify designing for high availability by aligning fault domains and update domains. You only have to define the fault domains count for the scale set. The number of fault domains available to the scale sets varies by region. Virtual machine scale sets are an Azure Compute resource you can use to deploy and manage a set of identical VMS. With all the VMS configured the same, VM scale sets are designed to support true auto-scale with no pre-provisioning of VMS. All VMS within a scale set are created from the same base OS image and configuration. Scale sets support the use of Azure Load Balancer for basic Layer 4 traffic distribution and Azure Application Gateway for more advanced Layer 7 traffic distribution and SSL termination. Scale sets are used to run multiple instances of your application. Scale sets support up to 1000 VM instances. If you create and upload your own custom VM images, the limit is 600 instances. Implementing scale sets. These are the considerations for implementing a scale set. A. Initial instance count, number of virtual machines in the scale set, 0 to 1000. B. Instance size of the virtual machine. C. Azure Spot instance. D. Use managed disks. Managed disks hide the underlying storage accounts and instead shows abstraction of a disk. Unmanaged disks expose the underlying storage accounts and VHD blobs. E. Enable scaling beyond 100 instances. If no, this scale set will be limited to one placement group and can have a max capacity of 100. If yes, the scale set can span multiple placement groups and max capacity of 1000, but changes the availability characteristics of the scale set. F. Spreading algorithm, max spreading or fixed spreading. Azure recommends max spreading for most workloads as this provides the best spreading in most cases. For implementing scale sets, first create load balancer. Then create virtual machine scale set in the same resource group as that of load balancer. Azure Dedicated Host is a service that provides physical servers which is able to host one or virtual machines dedicated to one Azure subscription. You can provision dedicated hosts within a region, availability zone, and fault domain. Then you can place VMS directly into your provisioned hosts. Virtual machine scale sets are not currently supported on dedicated hosts. Azure Dedicated Hosts provides the benefit of hardware isolation at the physical server level and control over maintenance events initiated by the Azure platform. No other VMS will be placed on your hosts. Dedicated hosts are deployed in the same data centers and share the same network and underlying storage infrastructure as no other non-isolated hosts. A host group is a resource that represents a collection of dedicated hosts. You create a host group in a region and availability zone and add hosts to it. A host is a resource mapped to a physical server in an Azure data center. The physical server is allocated when the host is created. A host is created within a host group. A host has a SKU describing which VM sizes can be created. Each host can host multiple VMS, of different sizes, as long as they are from the same size series. High availability considerations: for high availability, you should deploy multiple VMS spread across multiple hosts, minimum of 2. With Azure Dedicated Hosts, you have several options to provision your infrastructure to shape your fault isolation boundaries. Use availability zones for fault isolation. Availability zones are unique physical locations within an Azure region. Each zone is made up of one or more data centers equipped with independent power, cooling and networking. A host group is created in a single availability zone. Once created, all hosts will be placed in that zone. To achieve high availability across zones, you need to create multiple host groups, one per zone, and spread your hosts accordingly. If you assign a host group to an availability zone, all VMS created on that host must be created in the same zone. Use fault domains for fault isolation. A host can be created in a specific fault domain. Just like VM in a scale set or availability set, hosts in different fault domains will be placed on different physical racks in the data center. When you create a host group, you are required to specify the fault domain count. When creating hosts within the host group, you assign fault domain for each host. The VMS do not require any fault domain assignment. VMS deployed to hosts with different fault domains will have their underlying managed disk services on multiple storage stamps to increase the fault isolation protection. Using availability zones and fault domains, you can use both capabilities together to achieve even more fault isolation. In this case, you will specify the availability zone and fault domain count in for each host group, assign a fault domain to each of your hosts in the group and assign an availability zone to each of your VMS. Once a dedicated host is provisioned, Azure assigns it to a physical server. This curates the availability of the capacity WHE you need to provision your VM. Azure uses the entire capacity in the region, or zone, to pick a physical server for your host. Quotas: there is a default quota limit of 3000 VCPUs for dedicated hosts, per region. But the number of hosts you can deploy is also limited by the quota for the VM size family used for the host. If you want to request quota increase, select the Request Increase button in the upper right corner to file a request if needed. Pricing: users are charged per dedicated hosts, regardless how many VMS are deployed. The host price is set based on VM family, type, hardware size, and region. A host price is relative to the largest VM size supported on that host. Software licensing, storage and network usage are billed separately from the host and VMS. Virtual machine scale sets are not currently supported on dedicated hosts. The sizes and hardware types available for dedicated hosts vary by region. To deploy VMS to dedicated hosts, 1. Create a host group. Dedicated hosts can span across multiple availability zones. In this case, you are required to have a host group in each of the zones you wish to use. Span dedicated hosts across multiple fault domains which are mapped to physical racks. To create host groups Azure portal create a resource in the upper left corner search for host group and select host groups from the results in the host groups page, Select create equals equals, select the subscription and select create new equals equals, type in the resource group and select OK equals equals, type in the host group name equals equals, choose location equals equals, choose 1 for availability zone equals equals, choose 2 for fault domain count equals equals, click review plus create and create. To create a dedicated host equals equals, select create a resource in the upper left corner equals equals, search for dedicated hosts and then select dedicated hosts equals equals. In the dedicated host page, select create equals equals, select the subscription equals equals, select the resource group used while creating host groups equals equals, type in the host name and select location equals equals, select dedicated host family in the hardware profile. Equals, select host group equals equals, select 1 for fault domain equals equals, select review plus create and then create. To create a VM equals equals, choose create a resource in the upper left corner equals equals. In the new page, under popular, select Windows 2016 Dataset equals equals. In the basics tab, under project details, make sure correct subscription and dedicated host resource group is selected equals equals. Under instance details, type in the name for virtual machine and choose location equals equals. In the availability options, select 1 for availability zone equals equals. For the size, select change size and choose ESV3 series equals equals. Under administrator account, provide a username and password equals equals. Under inbound port rules, choose allow selected ports and then select RDP 3389 from the drop-down equals equals. At the top of the page, select the Advanced tab and in the host section, select my host group for the host group and my host for the host equals equals. Select Revo plus create and then create. The primary encryption-based disk protection technologies for Azure VMS are Storage Service Encryptio, SSE, add Azure Disk Encryption, AID. SSE is performed on the physical disks in the data center. If someone were to directly access the physical disk, the data would be encrypted. When the data is accessed from the disk, it is decrypted and loaded into memory. AID encrypts the virtual machine's virtual hard disk, VHDs. If the VHD is protected with AID, the disk image will only be accessible by the virtual machine that owns the disk. SSE is for data protection at rest. The Azure Storage Platform automatically encrypts data before it is stored to several storage services, including Azure Managed Disks. SSE encryption is enabled by default using 256-bit AES encryption and is managed by the storage account administrator. SSE is enabled by default for all new and existing storage accounts and cannot be disabled. SSE does not affect the performance of Azure storage services. Managed disks by default have SSE. AID is managed by the VM owner. It controls the encryption of Windows and Linux VM-controlled disks, using BitLocker on Windows and dmcrypt on Linux VMs. AID ensures that all data on VM disks are encrypted at rest in Azure Storage, and AID is required for VMs backed up to the recovery vault. With AID, VMs boot under customer-controlled keys and policies. AID is integrated with Azure Key Vault for the management of these disk encryption keys and secrets. AID does not support the encryption of basic tier VMs, and you cannot use an on-premise key management service with AID. AID is not available on basic A series VM, Generation 2 VMS, LSV2 series VMSS, or on Viridal Mcanis with a less than 2 GB of memory. AID also uses BitLocker and dmcrypt for its encryption. Even AID uses AES 256 encryption. Storage Service Encryption, SSE, is part of Azure itself, and there should be no noticeable performance impact on the VM disk I/O when using SSE. Managed disks with SSE is the default. SSE and AID encrypt at different layer, and serve different purposes. Both use AES 256 encryption. Before you can encrypt your VM disks, you need to A. Create a key vault, B. Set the key vault access policy to support disk encryption, C. Use the key vault to store the encryption keys for AID. The Azure Key Vault is a tool for securely storing and accessing secrets. A secret is anything that you want to tightly control access to, such as API keys, passwords, or certificates. This provides highly available and scalable sewer storage as defined in the Federal Information Processing Standards, FIPS, and I-140-2 Level 2 Validated Hardware Security Models, HSMs. 8 requires that your key vault and your VMS are in the same Azure region to ensure that encryption secrets do not cross regional boundaries. To create Key Vault, on the Azure portal, select Create a Resource. == Search for Key Vault. Click Create in the Details window == Enter the details of Key Vault. Enter the name for the Key Vault. Select the subscription. Select a resource group or create a new resource group to own the Key Vault. Select a location for the Key Vault same as that of VMS. Choose either standard or premium pricing tier. Premium tier allows for hardware encryption-backed keys. Change the access policies to support disk encryption == Select Access Policies. Click Advanced Access Policies. Click Enable Access to Azure Disk Encryption for volume encryption. Click Create. Azure needs access to the encryption keys or secrets in your Key Vault to make them available to the VM for booting of decrypting the volumes. There are 3 policies that you can enable. Disk encryption policy is required for Azure Disk Encryption. Deployment, optional, policy enables the Microsoft Compute Resource Provider to retrieve secrets from this Key Vault when this Key Vault is referenced in resource creation. For example, when creating a virtual machine. Template deployment, optional, policy enables Azure Resource Manager to get secrets from this Key Vault when this Key Vault is referenced in a template deployment. After setting up the Key Vault, you can encrypt the VM using Azure CLI or Azure PowerShell. On Windows VM, you can encrypt all disks or the OS disk only. On some Linux distributions only data disks can be encrypted. Windows disk must be formatted as NTFS volumes to be encrypted. Automation scripts are used to automate the deployment of scale sets and not related to automating the building of additional VMS in the scale set. To meet the requirements of setting up additional VMS when workload increases, you should create a scale set with auto scale option enabled. 2 products are available in Azure when you create a load balancer in Azure: A. Basic Load Balancer, B. Standard Load Balancers. Basic Load Balancer allow port forwarding, automatic reconfiguration, health probes, outbound connections through source network address translations, SNAT, and diagnostics through Azure Log Analytics for public-facing load balancers. Basic load balancers can be used only with VMS in a single availability set or a virtual machine scale set. Standard load balancers support all of the basic features. In addition, they allow HTTPS health probes, availability zones, diagnostics through Azure Monitor for multidimensional metrics, high availability ports, outbound rules, a guaranteed slot. Standard load balancer can use any virtual machines or virtual machine scale sets in a single virtual network. An external load balancer operates by distributing client traffic across multiple virtual machines. An external load balancer permits traffic from the Internet. The traffic might come from browsers, module apps, and other sources. An internal load balancer distributes a load from internal Azure resources to other Azure resources. No Internet traffic is allowed on internal load balancer. Azure Load Balancer is a service you can use to distribute traffic across multiple virtual machines. Use Load Balancer to scale applications and create high availability for your virtual machines and services. Load balancers use a hash-based distribution algorithm. By default, a 5-tuple hash is used to map traffic to available servers. The hash is made of source IP, source port, destination IP, destination port, and protocol types such as TCP or UDP. Load balancers are not physical instances. Load balancer objects are used to express how Azure configures its infrastructure to meet your requirements. To achieve high availability with Load Balancer, you can choose to use availability sets and availability zones to ensure that virtual machines are always available. SLA for availability set is 99.95%, protection from hardware failures within data centers, while SLA for availability zone is 99.99%, Protection from entire data center failure. Availability set is a logical grouping that you use to isolate volatile machine resources from each other when they are deployed. Azure ensures that the volatile machines you put in an availability set are used across multiple physical servers, compute racks, storage units and network switches. If there is a hardware or software failure, only a subset of your virtual machines is affected. Availability zones offer groups of one or more data centers that have independent power, cooling and networking. The virtual machines in an availability zone are placed in different physical locations within the same region. Use this architecture when you want to ensure that, when an entire data center fails, you can continue to serve users. Availability zones do not support all virtual machine sizes and are not available in all Azure regions. Load Balancer supports both basic and standard SKUs. These SKUs differ in scenario scale, features, and pricing. Any scenario that is possible with basic load balancer is possible with standard load balancer. A public load balancer maps the public IP address and port number of incoming traffic to the private IP address and port number of a virtual machine in the back-end pool. By applying load balancing rules, you distribute specific types of traffic across multiple virtual machines or services. By default, Azure Load Balancer distributes network traffic equally among virtual machine instances. The following distribution modes are also available if a different behavior is needed. A 5-tuple hash is the default distribution mode for Azure Load Balancer. The tuple is composed of the source IP, source port, destination IP, destination port, and protocol type. Because source port is included in the hash and the source port changes for each session, clients might be directed to a different virtual machine for each session. B. Source IP affinity, also known as session affinity or client IP affinity. To map traffic to the available servers, the mode uses a 2-tuple hash, from the source IP address and destination IP address, or 3-tuple hash, source IP, destination IP, and protocol type. The hash ensures that requests from a specific client are always sent to the same virtual machine behind the load balancer. If the requirement of the presentation tier is to use in-memory sessions to store the logged user's profile as the user interacts with the portal, then the load balancer must provide source IP affinity to maintain a user's session. The profile is stored only on the virtual machine that client first connects to because that IP address is directed to the same server. In Azure Portal, this is done by specifying the value of an IP for session persistence to client IP. Remote Desktop Gateway is a Windows service that you can use to enable clients on the Internet to make RDP connections through firewalls to remote desktop servers on your private network. The default 5-tuple hash in Load Balancer is incompatible with this service. If you want to use Load Balancer with your remote desktop server, use source IP affinity. When you create a public load balancer, you must also create a public IP address that is configured as the front end for the load balancer. The load balancer resources are the backend address pool, a health probe, and a balancer rule. The backend address pool contains the IP addresses of the NICs of the VMS. To create backend pool in Azure Portal, select all services all resources select the load balancer created under settings select add create a backend pool. To allow the load balancer to monitor the status of URAP, you use a health probe which dynamically adds or removes VMS from the load balancer rotation based on their response to health checks. Public IP SKUs and load balancer SKUs must match. For standard load balancer, use VMS with standard IP addresses in the backend pool. Application Gateway manages the requests the client applications can send to a web app. Application Gateway routes traffic to a pool of web servers based on the URL of a request. This is known as application layer routing. The pool of web servers can be Azure Virtual Machines, Azure Virtual Machine Scale Sets, Azure App Service, and even on-premise servers. Before a client sends a request to an application gateway, it resolves the domain name of the application gateway by using a DNS server. Azure control the DNS entry because application gateways are in the azure.com domain. The Azure DNS returns the IP address to the client, which is the front-end IP address of the application gateway. The application gateway accepts incoming traffic on one or more listeners. A listener is a logical entity that checks for connection requests. It is configured with a front-end IP address, protocol and port number for connections from clients to the application gateway. If a web application firewall is in use, the application gateway checks the request headers and the body, if present, against the WAF rules. This action determines if the request is a valid request or a security threat. If the request is valid, it is routed to the backend. If the request is not valid and WAD is in prevention mode, it is blocked as a security threat. If it is in detection mode, the request is evaluated and logged, but still forwarded to the backend server. Azure Application Gateway can be used as an internal application load balancer or as internet-facing application load balancer. An internet-facing application gateway uses public IP addresses. The DNSAE of an internet-facing application gateway is publicly resolvable to its public IP address. As a rule, internet-facing application gateways can route clients' requests to the internet. Application gateway has several components. The main parts for encryption are the front-end port, the listener, and the backend pool. Traffic enters the gateway trough a front-end port. You can open many ports and application gateway can receive messages on any of these ports. A listener is the first thing that your traffic meets when entering the gateway through a port. It is set up to listen for a specific host name, and specific port on a specific IP address. The listener can use an SSL certificate to decrypt the traffic that enters the gateway. The listener then uses a rule that you define to direct the incoming requests to a backend pool. The backend pool contains your application servers. These servers might be virtual machines, a virtual machine scale set, or applications running on Azure App Service. Incoming requests can be load balanced across the servers in this pool. The backend pool has an HTTP setting that references a certificate used to authenticate the backend servers. The gateway re-encrypts the traffic by using this certificate before sending it to one of your servers in the backend pool. If you are using Azure App Service to host the backend application, you don't need to install any certificates in Application Gateway to connect to the backend pool. All communications are automatically encrypted. Application Gateway trusts the servers because Azure manages them. Client sends requests to your web apps to the IP address or DNS name of the gateway. The gateway routes requests to a selected web server in the backend pool, using a set of rules configured for the gateway to determine where the request should go. There are two primary methods of routing traffic: path-based routing and multiple site hosting. Path-based routing enables you to send requests with different paths in the URL to a different pool of backend servers. Multiple site hosting enables you to configure more than one web application on the same application gateway instance. In a multi-site configuration, you register multiple DNS names, for the IP address of the application gateway, specifying the name of each site. Application Gateway uses separate listeners to wait for requests for each site. Each listener passes the request to a different rule, which can route the requests to servers in a different back-end pool. Multi-site configurations are useful for supporting multi-tenant applications, where each tenant has its own set of virtual machines or other resources hosting a web application. Additionally, Application Gateway can use redirection, can rewrite HTTP headers and create custom error pages. Application Gateway has a series of components that combine to route requests to a pool of web servers and to check the health of these web servers. The series of components which make an application gateway are front-end IP address, listeners, routing rules, back-end pools, WAF, health probes. Client requests are received through a front-end IP address. You can configure an application gateway to have a public IP address, a private IP address, or both. Application Gateway cannot have more than one public and one private IP address. Application Gateways uses one or more listeners to receive incoming requests. A listener accepts traffic arriving on a specified combination of protocol, port, host, and IP address. Each listener routes requests to a backend pool of servers following routing rules that you specify. Each listener routes requests to a backend pool of servers following routing rules that you specify. A listener can be basic or multi-site. A basic listener routes a request based on the path in the URL. A multi-site listener can also route requests using the hostname element of the URL. A routing rule binds a listener to the backend pools. A rule specifies how to interpret the hostname and path elements in the URL of a request and direct the request to the appropriate backend pool. A route rule has an associated set of HTTP settings. These settings indicate whether traffic is encrypted between application gateway and the backend servers and other configuration information such as protocol, session stickiness, connection draining, request timeout period, and health probes. A backend pool references a collection of web servers. You provide the IP address of each web server and the port on which it listens for requests when configuring the pool. Each pool can specify a fixed set of virtual machines, a virtual machine scale set, an app hosted by Azure App Services, or a collection of on-premises servers. Each back-end pool has an associated load balancer that distributes the work across the pool. WAF is an optional component that handles incoming requests before they reach a listener. The WAF checks each request for many common threats, based on the OWASP. These include SQL injection, cross-site scripting, commit injection, HTTP request smuggling, HTTP response splitting, remote file inclusion, bots, crawlers, and scanners, and HTTP protocol violations and anomalies. WAF is enabled on your application gateway by selecting the WAF tier when you create a gateway. If you don't configure a health probe, Application Gateway creates a default probe that waits for 30 seconds before deciding that a server is unavailable. A container provides a grouping of a set of blobs. All blobs must be in a container. An account can contain an unlimited number of containers. A container can store unlimited number of blobs. Container is created via the Azure portal or PowerShell. Public access level for a container could be private, no anonymous access to containers and blobs, or blob, anonymous public read access for blobs only, or container, anonymous public read and list access to entire container including blobs. Blob access tiers are for accessing blob data based on usage patterns. These access tiers can be hot, cool, or archive. Hot for frequent access of objects in the storage account. Accessing data in the hot tier is cost-effective, but storage is expensive. New storage accounts are created in the hot tier by default. Cool tier is optimized for storing large amounts of data that is infrequently accessed and stored for at least 30 days. Storing in cool tier is cost-effective, but accessing it is expensive. Archive tier is optimized for data that can tolerate several hours of retrieval latency and will remain on archive tier for 180 days. If there is a change in usage pattern of your data, you can switch between these access tiers at any time. Azure Blob Storage Lifecycle Management offers a rich, rule-based policy for GPv2 and blob storage accounts, which can be used to transition the data to the appropriate access tiers or let it expire at the end of the data's life cycle. This policy lets you define rules that can be applied to containers or a subset of blobs. If data gets accessed frequently during early stages of the life cycle, and not after 2 weeks, then hot tier storage is best for early stages. Cool tier storage is best for occasional access. Archive tier storage is best after data ages over a month. A blob can be any type and size file. Azure Storage offers 3 types of blobs: block blobs, page blobs, and append blobs. You specify the blob type and access tier when you create the blob. Block blobs consists of blocks of data assembled to make a blob. Most scenarios using blob storage employ block blobs. Block blobs are ideal for storing text and binary data in the cloud, like files, images and videos. Append blobs are like block blobs in that they are made up of blocks, but they are optimized for append operations, so they are useful for logging scenarios. Page blobs can be up to 8 TB in size and are more efficient for frequent read/write operations. Azure virtual machines use page blobs as OS and data disks. Once the blob has been created, its type cannot be changed. Blob upload tools. AZCopy is an easy-to-use command line tool for Windows and Linux that copies data to and from blob storage across containers and storage accounts. The Azure Storage Data Movement Library is a .NET library for moving data between Azure storage services. The AZCopy utility is built with the Data Movement Library. Azure Data Factory supports copying data to and from blob storage by using account key, shared access signature, service principal, or managed identities for Azure Resources authentication. BlobFuse is a virtual file system driver for Azure Blob Storage. You can use BlobFuse to access your existing blob data in your storage account through Linux file system. Azure Data Box Disk is a service for transferring on-premises data to blob storage when large datasets or network constraints make uploading data over the wire unrealistic. You can Azure Data Box Disk to request solid-state disks from Microsoft. You can then copy your data to those disks and ship them back to Microsoft to be uploaded into blob storage. The Azure Import/Export service provides a way to export large amounts of data from your storage account to hard drives that you provide and that Microsoft ships back to you with your data. In addition to these, you can always use Azure Storage Explorer. Storage pricing, performance tiers. In addition to the amount of data stored, the cost of storing data varies depending upon the storage tier. The per gigabyte cost decreases as the tier gets cooler. Data access costs. Data access charges increase as the tier gets cooler. For data in the cool and archive storage, per gigabyte data access charges are charged for reads. Transaction costs. There is per transaction charge for all tiers that increases as the tier gets cooler. Georeplication data transfer costs, applies to such accounts with georeplication configured, including GRS and RAGRS. Georeplication data transfer incurs a per gigabyte charge. Outbound data transfer costs. Outbound data transfers out of an Azure region incur billing for bandwidth usage on a per gigabyte basis, consistent with general purpose storage accounts. Changing the storage tier. Changing the account storage tier from cool to hot incurs a charge equal to reading all the data existing in the storage account. However, changing the account storage tier from hot to cool incurs a charge equal to writing all the data into the cool tier, GPv2 only. Azure File Storage offers shared storage for applications using the industry standard SMB protocol. Microsoft Azure virtual machines and cloud services can share file data across application components via mounted shared, and on-premises applications can also access file data in the share. Common uses of file storage are: A. Replace and supplement. Azure files can be used to completely replace or supplement traditional on-premises file servers or NAS devices. B. Access anywhere. Windows, Mac OS, Linux can directly mount Azure file shares concurrently by cloud or on-premises wherever they are in the world. C. Lift and shift. Applications can be lifted and shifted to the cloud that expect a file share to store file application or user data. D. Azure File Sync. Azure file shares can also be replicated with Azure File Sync to Windows servers, either on-premises or in the cloud, for performance and distributed caching of the data where it is being used. E. Shared application. Storing shared application settings, for example in configuration files. F. Diagnostic data. Storing diagnostic data such as logs, metrics, and crash dumps in shared location. G. Tools and utilities needed for developing or administering Azure virtual machines or cloud services. Azure Files provides an SMB, server message block protocol, interface, client libraries, and a REST interface that allows access from anywhere to stored files. Suitable for lift and shift applications to the cloud that already uses the native file system APIs to share data between it and other applications running in Azure, and for development debugging tools that need to be accessed from many virtual machines. Azure Blobs provides client libraries and a REST interface that allows unstructured data to be stored and accessed at a massive scale in block blobs. Suitable for streaming and random access scenarios from anywhere. Azure files are true directory objects. Azure Blobs are a flat namespace. Azure files are accessed through file shares. Azure Blobs are accessed through a container. Azure files provide shared access across multiple virtual machines. Azure disks are exclusive to a single virtual machine. For Azure file shares, port 445 must be open for SMB protocol over TCP. Azure file shares can be mounted in Linux distributions using the CIFS kernel client. File mounting can be done on demand with the mount command or on boot, persistent, by creating an entry in /etc/fstab. Secure transfers can enable to file shares using HTTPS. HTTP will be rejected when secure file transfer required is enabled. File storage tiers, 4 tiers, Premium, Transaction Optimized, Hot, and Cool. Premium tier, premium file shares are backed by SSD and provide consistent high performance and low latency within single-digit milliseconds for most I/O operations for I/O-intensive workloads. Premium file shares are suitable for a wide variety of workloads such as databases, website hosting and dev environments. Can be used with SMB and NFS protocols. Transaction Optimized, enable transaction-heavy workloads that don't need the latency offered by premium file shares. Use HDDs. Hot file shares offer storage optimized for general-purpose file sharing scenarios such as team shares. Backed by HDDs. Cool tier, offer cost-efficient storage optimized for online archive storage scenarios. Backed by HDDs. Both hot and cool tiers are also standard tiers because they are on standard storage hardware backed by HDDs. With SSE, Azure Platform automatically encrypts the data before persisting it to the Azure Managed Disks, Azure Blob, Queue, Table Storage, or Azure Files and decrypts the data before retrieval. The handling of encryption at rest, decryption, and key management in SSE is transparent to users. All data written to the Azure Storage Platform is encrypted through 256-bit AES encryption. SSE is enabled for all new and existing storage accounts and cannot be disabled. If you prefer, you can use the Azure Key Vault to manage your encryption keys. With the Key Vault, you can create your own encryption keys and store them in a Key Vault, or you can use Azure Key Vault's API to generate encryption keys. To use customer-managed keys with SSE, you can either create a new Key Vault or you can use existing Key Vault and key. The storage account and the Key Vault must be in the same region, but can be in different subscriptions. Azure storage accounts can create authorized apps in Active Directory to control access to the data in blobs and queues. Alternatively, a shared key or shared secret method can also be used for blobs, files, queues and tables by making client embed the shared key in the HTTP authorization header of every request and making the storage account validate it. Shared keys in Azure storage accounts are called storage account access keys. Azure creates 2 of these keys, primary and secondary, for each storage account you create, and they give access to everything in the account. Because there are only 2 keys and they provide full access to the account, it is recommended to only use these keys with trusted in-house applications that you have complete control over. If the keys are compromised, you can change the key values in Azure Portal. You might regenerate these storage account keys on a regular basis as a policy, or if the keys are compromised, or if your team is using Storage Explorer application that retains the storage account key and one of the team member leaves. The process to refresh keys is simple. Change each trusted app to use the secondary key. Refresh the primary key in the Azure portal. Any client using the old key value will be refused. A shared access signature, SAS, is a URI that grants restricted access rights to Azure storage resources such as a specific blob. You can provide a shared access signature to clients who should not be trusted with your storage account key but whom you wish to delegate access to certain storage account resources. By distributing a shared access signature URI to these clients, you grant them access to a resource for a specified period of time. A SAS gives you granular control over the type of access you grant to clients who have the SAS, including a. Account-level SAS that can delegate access to multiple storage services such as blob, table, or queue, or file. B. An interval over which the SAS is valid by including start time and the expiry time. C. The permissions granted by the SAS. For example, a SAS for a blob might grant read-write permissions to that blob, but not delete permission. D. Optionally, you can also specify an IP address or a range of IP addresses from which Azure Storage will accept the SAS. E. The protocol over which Azure Storage will accept the SAS. The URI contains storage resource URI and the SAS token. The SAS token includes storage services version, services, resources types, start time, expiry time, resource, permissions, IP range, protocol, signature, etc. There are two types of SAS, account and service. The account SAS delegates access to resources in one or more storage services. The service SAS delegates access to a resource in just one of the storage services. A stored access policy can provide an additional level of control over service-level SAS on the server side. You can group shared access signatures and provide additional restrictions for signatures that are bound by the policy. Authorizing requests against Azure Storage with Azure AD provides superior security and ease of use over shared key authorization. Microsoft recommends using Azure AD authorization with your blob and queue applications when possible to minimize potential security vulnerabilities inherent in shared key. Authorization with Azure AD is available for all general-purpose and blob storage accounts in all public regions and national clouds. Only storage accounts created with the Azure Resource Manager deployment model support Azure AD authorization. Authorization with Azure AD is not supported for Azure Table Storage. Use shared key to authorize requests to table storage. With Azure AD, access to a resource is a two-step process. First, the security principal's identity is authenticated and an OAuth 2.0 token is returned. Next, the token is passed as part of a request to the blob or queue service and used by the service to authorize access to the specified resource. The authentication step requires that an application request an OAuth 2.0 access token at runtime. If an application is running from within an Azure entity such as an Azure VM, a virtual machine scale set, or an Azure Function app, it can use a managed identity to access blobs or queues. The authorization step requires that one or more RBAC roles be assigned to the security principal with relevant permissions. Native applications and web applications that make requests to the Azure Blob or Queue service can also authorize access with Azure AD. Azure Storage defines a set of built-in RBAC roles that encompass common sets of permissions used to access blob and queue data. You can also define custom roles for access to blob and queue data. Access can be scoped to the level of subscription, the resource group, the storage account, or an individual container or queue. Built-in RBAC roles for blob and queues are Storage Blob Data Owner, Storage Blob Data Contributor, Storage Blob Data Reader, Storage Queue Data Contributor, Storage Queue Data Reader, Storage Queue Data Message Processor, Storage Queue Data Message Sender. The following list describes the levels at which you can scope access to Azure Blob and Queue resources, starting with narrowest scope. A. At individual container. B. At individual queue. C. The storage account. D. The resource group. At this scope, a role assignment applies to all of the containers or queues in all of the storage accounts in the resource group. E. The subscription. At this scope, a role assignment applies to all of the containers or queues in all of the storage accounts in all of the resource groups in the subscription. Access to blob or queue data via the Azure portal, PowerShell, or Azure CLI can be authorized by using the user's Azure AD account by using the account access keys, shared key authorization. When you attempt to access blob or queue data, The Azure portal first checks whether you have been assigned an RBAC role with Microsoft.storage/storage-accounts/list-keys/action. If you have been assigned a role with this action, then the Azure portal uses the account key for accessing blob and queue data via shared key authorization. If you have not been assigned a role with this action, then the Azure portal attempts to access data using your Azure AD account. To access blob or queue data from the Azure portal using your Azure AD account, you need permissions to access blob and queue data, and you also need permissions to navigate through the storage account resources in the Azure portal. The built-in roles provided by Azure Storage grant access to blob and queue resources, but they don't grant permissions to storage account resources. Access to the portal also requires the assignment of an Azure Resource Manager role such as the reader role, scoped to the level of storage account or higher. The reader role grants the most restricted permissions, but any other Azure Resource Manager role that grants access to storage account management resources is also acceptable. If a SAS is compromised, it can be used by anyone who obtains it. Always use HTTPS to create or distribute a SAS. Reference stored access policies where possible. Stored access policies give you the option to revoke permissions without having to regenerate the storage account keys. Set the expiration on these very far in the future and make sure it is regularly updated to move it farther into the future. Use near-term expiration times on an ad hoc SAS. Have clients automatically renew the SAS if necessary. Set the SAS start time to 15 minutes in the past to avoid issues of clock skew. Be specific with the resource to be accessed. Understand that your account will be billed for any usage, including that done with SAS. Validate data written using SAS. Don't assume SAS is always the correct choice. Use storage analytics to monitor your application. To create a SAS. Azure portal == locate the store account you want to work with and open it. == blob container == click the file you would like to provide access to. == generate SAS tab == configure SAS using the following parameters == permissions, start and expiry date time, allowed protocols, signing key == copy the blob server SAS URL in the browser and verify that the blob file displays == this is for creating SAS at the service level. To create SAS at the account level == return to your storage account == click shared access signature == notice you can configure a variety of services, resource types, and permissions. == click generate SAS and connection string == review the connection string, SAS token, and URL information that is provided. Storage accounts have a public endpoint that is accessible through the internet. You can also create private endpoints for your storage account, which assigns a private IP address from your VNet to the storage account and secures all traffic between your VNet and the storage account over a private link. The Azure Storage Firewalls provides control access for the public endpoint of your storage account. You can also use the firewall to block all access through the public endpoint when using private endpoints. Your storage firewall configuration also enables select trusted Azure platform services to access the storage account securely. To secure your storage account, you should first configure a rule to deny access to traffic from all networks, including internet traffic, on the public endpoint by default. Then you should configure rules that grant access to traffic from specific VNets. You can also configure rules to grant access to traffic from select public Internet IP address ranges, enabling connections from specific Internet or on-premise clients. This configuration enables you to build a secure network boundary for your applications. You can combine firewall rules that allow access from specific virtual networks and from public IP address ranges on the same storage account. Storage firewall rules can be applied to existing storage accounts, or when creating new storage accounts. Storage firewall rules apply to the public endpoint of a storage account. You don't need any firewall access rules to allow traffic for private endpoints of a storage account. Network rules are enforced on all network protocols to Azure Storage including REST and SMB. To access data using tools such as the Azure Portal, Storage Explorer, and AZ Copy, explicit network rules must be configured. Once network rules are applied, they are enforced for all requests. SAS tokens that grant access to a specific IP address serve to limit the access of the token holder, but don't grant new access beyond configured network rules. Virtual machine disk traffic is not affected by network rules. REST access to page blobs is protected by network rules. Classic storage accounts do not support firewalls and virtual networks. To manage default network access rules using Azure Portal == go to the storage account you want to secure == click on the settings menu called Firewalls and Virtual Networks == to deny access by default, choose to allow access from selected networks. To allow traffic from all networks, choose to allow access from all networks. Save your changes. You can configure storage accounts to allow access only from specified subnets either in the same subscription or in a different subscription or a different Azure Active Directory tenant. Enable a service endpoint for Azure storage within the VNet. The service endpoints route traffic from the VNet through an optimal path to the Azure storage service. The identities of the subnet and a virtual network are also transmitted with each request. Administrators can then configure network rules for the storage account that allow requests to be received from specific subnets in a VNet. Clients granted access via these network rules must continue to meet the authorization requirements of the storage account to access the data. In general, service endpoints work between virtual networks and service instances in the same Azure region or paired region. Service endpoints allow continuity during a regional failover and access to RAGRS instances. When planning for disaster recovery during a regional outage, you should create the VNets in the paired region in advance. Service endpoints do not apply to traffic outside the region of the virtual network and the designated region pair. You can only apply network rules granting access from virtual networks to storage accounts in the primary region of a storage account or in the designated paired region. To apply a virtual network rule to a storage account, the user must have the appropriate permissions for the subnets being added. The permission needed is join service to a subnet and is included in the storage account contributor built-in role. Storage account and the virtual networks granted access may be in different subscriptions, including subscriptions that are part of a different Azure AD tenant. Configuration rules that grant access to subnets in virtual networks that are part of a different Azure Active Directory tenant are currently only supported through PowerShell, CLI, and REST APIs. Such rules cannot be configured through the Azure portal, though they may be viewed in the portal. IP network rules have no effect on requests originating from the same Azure region as the storage account. Use virtual network rules to allow same region requests. Services deployed in the same region as the storage account use private Azure IP addresses for communication. Thus, you cannot restrict access to specific Azure services based on their public outbound IP address range. Only IPv4 addresses are supported for configuration of storage firewall rules. To grant access from your on-premise networks to your storage account with an IP network rule, you must identify the internet-facing IP addresses used by your network. If you are using Express Route from your premises, for public peering or Microsoft peering, you will need to identify the NAT IP addresses that are used. For public peering, each Express Route circuit by default uses two NAT IP addresses applied to Azure service traffic when the traffic enters the Microsoft Azure network backbone. For Microsoft peering, the NAT IP addresses used are either customer provided or are provided by the service provider. To allow access to your service resources, you must allow these public IP addresses in the resource IP firewall setting. Securing storage endpoints == 1. Create storage account in the portal 2. Upload a file to the storage account. 3. Create a subnet service endpoint 4. Secure the storage to the service endpoint. 5. Test the storage endpoint to create storage account through portal == in the Azure portal. select all services select storage accounts click add select subscription create or choose existing resource groups select location for your storage account click review plus create click create upload a file to the storage account within the storage account, create a file share and upload a file for the storage account. Use the shared access signature blade to generate SAS and connection string use Storage Explorer and the connection string to access the file share. Create a subnet service endpoint select your virtual network, then select a subnet in the virtual network. Under service endpoints, view the services drop-down and different services that can be secured with an endpoint check the Microsoft.storage option save your changes. Secure the storage account to the service endpoint return to the storage account select firewalls and virtual networks change to selected networks add existing virtual network, verify your subnet with the new service endpoint is listed save your changes.